start doing that now. So yeah, recording physics classes. Yeah, we're going to do attendance. I'm going to show you a little bit of the Google Classroom. Some of you have logged into it, some of you have not. If you could do me a favor, did I turn this down? Yeah, if you could do me a bit of a favor today, after I've posted the video, I'll be posting them in YouTube, and then bringing those links into the Google Classroom, because I have been told that if I do it that way, you guys are able to watch it at an increased speed, should you desire to do that. And if you want to hear my voice at 2 times speed, and at least have the option to do it that way, that is vastly preferable. So I'm going to do it that way. Please, if you can, today or tomorrow, sometime in the next couple days, watch one of these videos or even a part of one of these videos on whatever device you would likely watch it on, and then let me know the audio. Basically, I've had issues with audio in the past with different devices. Brendan, I think it was your grade 9 class, that was the beginning of the audio problems. So if you can do that for me, that'd be great. If I hear nothing, I'll assume that the audio is all good. So attendance first, and then we're going to get into things. The attendance question for today is this, if my computer ever loads things. Yes, verify that it's me. That would just make my day. Your question of the day is this. Oh, for the love. Let's go. There we go. We're going to jump right into like the deeply personal stuff. If you could pick, it's 2 options. Okay? Either the actor that plays you in the movie of your life, or who narrates the movie that is your life. Okay? So who's the lead actor who plays you, or actress, or who narrates? Who's the voiceover for the movie that is your life? Okay? That's the question for today. I'll go with you. Jazz. Sorry, and because you're all wearing masks, I need more than just eye contact because everyone's looking at me. Where's Jazz? Hey, Jazz. Ryan Reynolds to play you and to do the narration. Okay. Ryan Reynolds is going to be you. Okay. Jazz, up or down? Okay. Tenjo. Or Tenjo. Yeah, Tenjo. To play you or to voice you over? The voiceover. Love it. Khalil. Sorry, Samuel L. Jackson to do what? The voiceover? Love it. Tristan, you back? I love it. Naya. I'll kill that off your ass in a sec.
I don't know. I love Jessica Alba, so I guess her.
Jessica Alba does the narration of your life. Okay. Abdul. Mr. Peters, what's up? Yeah, you need me out there or over here? Okay, I will pause my recording. Okay, back to this. Where were we? I was on... okay. I said this wrong yesterday. Is it Iman? Iman. Sorry, Iman. Jake Paul. Jake Paul, like the YouTuber, is going to do... He's going to act as you. He's going to play you. Okay, interesting. Kenwar. To do what? Brad Pitt's going to be you in the movie of your life. Okay. Brendan. David Attenborough, great choice. We all know who David Attenborough is? No. Who said no? You have no idea who David Attenborough is? Okay, hold on. Yeah, you're going to recognize it as soon as you hear it. It's a solid answer. David Attenborough. Come on. There we go. Hey guys.
Ants are among the most numerous, widespread, and frequently exploited members of the undergrowth. These, in Australia, collect seeds and store them underground.
This guy, who is, fun fact, he is the brother of the old, not of Morgan Freeman, of the, if you've seen the original Jurassic Park, the old guy, that's his brother. Also, he played Santa Claus in The New Miracle on 34th Street. Also, his, like, they're, yeah. This guy and that guy are brothers. The Attenboroughs have fantastic voices, both of them. So Smallenberg. Ravneet. Angelina, to play you? Angelina's going to be you, okay? Niraj. Nice. Luis. Sorry? Okay, I don't know who that is, but that's cool. Kirat. Emma Watson as the voice of the narrator of your life. Okay, Indu. You got nothing for me? Okay. Connor.
Robert De Niro for narrator.
Nice. Ahmad. Okay, who's that?
He's the actor of he's Aladdin.
Oh, he's Aladdin. To play you or to voice you over? Nice. Hershan.
Leonardo
DiCaprio. Love it. Play you or voice over? Okay. Manuel.
I want Joe Rogan to be narrator.
Joe Rogan is going to narrate. Okay, that's a controversial figure. Anaya. Reese Witherspoon. What have you seen Reese Witherspoon in? I feel like she's like a post or pre your generation. Okay. Okay. Yeah, I didn't realize people still watched Legally Blonde. Yeah, she is Legally Blonde. But Legally Blonde is like 20 years old. Okay, still iconic. Okay, fair enough. Cohen. Adam Sandler. To play you or to voice you over? Okay. Angelina. Oh, there it is in absence. Gurpreet. Love it. Zaid.
Like a young Harrison Ford.
To do what?
Act.
Okay. Jasmine. Zendaya. Or Zendaya? To do what? Both. Okay. Autumn.
I would want to be myself.
That's not an option. Well, then you need a narrator to be not you.
Well, I would narrate too.
No, that's not the question.
But that's what I would do.
That's not an option, though.
Maybe though.
Sorry?
I wouldn't have anyone like.
No, you be you, but someone else has to voice over.
I would play myself and I would voice over it myself.
No. Someone else has to do one of those two things.
Yeah, Shudder Khan.
Okay. James.
The Rock.
The Rock. Okay. Eric. Is he over there? Eric, are you here? You're also going to say The Rock. There you go. Anmo.
I was gonna say David Attenborough too.
You also say David Attenborough. Nice. So I've just got Angelina and Gurpreet away, which means there's 25 of you here. Cool. Love it. Oh, Tristan. You're still on my list, man.
No?
Yeah, no. But we'll go for it. Tristan, what do you got for us? Who's going to play you, or who's the voice that narrates the movie that is your life?
A young Matt Damon.
A young Matt Damon to play. I can see that. Young Matt Damon. Okay. I go with Jeremy Irons to do the narration for my life. I don't know. See if you tell me if you recognize this voice. Wait for it. Come on, YouTube. I believe in you. I have to find a video that's not horribly inappropriate. Oh, you know what? One of these voices will be him. Okay, let's see what he has to say about this one. This is him on Conan O'Brien, so I don't know if this is actually going to be appropriate or not.
Or Catcher Now. All right, my first guest is an Academy Award-winning actor, and beginning this Friday, you can see him.
Okay, just stop talking, Conan.
I like the way you're dressed. This is,
You do?
Yeah, this is unusual. It's
Well,
fantastic.
I knew you'd be wearing a collar and tie, and I thought, let's have a little bit of contrast.
Right. Let's.
Does anyone recognize that voice? Who is he?
I have no clue, but I recognize.
Where's you heard it?
I don't remember.
He's the voice of Scar in The Lion King. He's the guy who voices Scar from The Lion King. I've always thought he's got a fantastic voice, and he's great in some of his more dramatic roles. That is who would be the narration for the movie that is my life. That'd be cool. Anyway. Okay, here we go. So I'm gonna hand out a bunch of stuff. Yesterday we went over the course outline, and I said I wanted you to take a copy of it home. Your parents can go over it and sign, and you're also going to sign. So here it is. Here is the course outline. 1, 2, 3, 4, 5, 6, 7. Taking fast keys. 1, 2, 3, 4, 5, 6, 7. Take the whole. Yeah, all of y'all. 7 more. 1, 2, 3, 4, 5, 6, 7. 5. 1, 2, 3, 4, 5. There you go. Thank you. If any of you have finished your student info sheets and want to hand those back in to me, that would be lovely. Anything you guys are going to hand in to me, you can't access it right now. So I'll take it if you want to get those out.
I want to break it all out.
This thing, if you finish this, if you took it home and finished this, I want them back. If it's not done, get it done. Return to me, please. That would be lovely. And of course, outlines are there. That's great. The next thing I'm going to give you all is this. You all are going to get a copy of the formula sheet. We'll talk it through in a second here, but here it is. Don't lose this. 1, 3, 4, 5, 6, 7. Tristan, I think there was someone or was it this is whole mess here. Never mind, Tristan, you're good. 1, 2, 3, 4, 5, down. Okay, so the formula sheet, the short one. Okay. You pass that back. Okay, so you want a paper copy? Yeah, formula sheet? Okay. So this formula sheet, the extra, you must have a paper copy. This is the extra. It's running on the background. You've got it here. Okay, so the formula sheet, the reason you all gotta have a paper copy of the formula sheet is because I'm not gonna let you use your iPad on test. This formula sheet, the one I've just handed to you, we'll be making notes on as we go. Anything that I write on the formula sheet, you may also write on the formula sheet, and then this is the formula sheet that you will be allowed to use on the tests and quizzes that we do. So if you have my notes, great. The things that we've added here. If you don't, well, it's going to suck when I give you a blank one. You're like, but I don't have any of the notes. And I said, well, you lost it. That's not my problem. So this is the vast majority of the stuff. We're going to go through it over the course of the semester. There's some constants at the top. There's a table of specific heat capacities and some refractive indices there if we get through optics. Some math formulas there that might be useful to you for those of you who've forgotten how to find the area of a triangle. All of that might be useful to you. The conversions, we'll talk about those hopefully today. Boom, boom. I think I got all that. Hands up if you would be interested in one of these to use for this. Okay, fantastic. Here we go. Let's do this. They're all 200 pages? They're big. Yeah, they're all big? Cool. The office accident ordered me the wrong size. They ordered the bigger size to the smaller, which might actually be useful to you. Well, that's not what I prefer, but it might be great for you guys. It's just This is how big they are, and this is how big I wanted them to be. So whatever. If you would like one, so that you know, all crowding around Naya. They're different colors. I don't particularly care what color you get or want. If there's a purple one, you're gonna have to find it. If you want one, come get one. There are different colors. Go nuts. Here. Please take only one, because I need them for some of my other classes as well. Okay, so if you, 80 pages, or the 200 pages should last you the vast majority of the semester. By the same point you run out, let me know, I'll get you another one. The last thing I think I'm going to give you today is this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Don't give anything to him. Not one of these. 1, 2, 3, 4, 5. You're doing it all on there, yeah? This is the PDF. The thing I just handed out is the PDF. So, actually, I need a copy of this. Okay, so let's start. We're going to start Physics 11 today. Hopefully you brought things to write with, and I've provided you with things to write on. Let's see if you've been added back to my list yet, Tristan. There you are. Tristan, you're back on the list. I love how quickly that happens. You were out, and then you were in, and then you were out again. Now you're in again. Love it. Okay, so the formula sheet's going to be useful to you guys, like I've said. Depending on what we are doing, there's a bunch of different constants here that are going to show up. We're going to do a lab where you guys actually have to find this. That's going to be cool. See how close you get. The specific heat capacities, these guys are going to show up when we do thermal energy. I don't know if you're aware, maybe you are, especially if you've ever worked you've done any cooking at all at home. Different materials absorb heat differently. And so this is related to all of that. It's the amount of energy required to change the kilogram of a substance a degree. So water requires a lot of energy to change, and a kilogram of water is a liter. It takes a lot of energy to change a kilogram of water 1 degree Celsius. So that's what that's going to be. The table of refractive indices. Different materials cause light to travel at different speeds. So we're going to look at that there. I'm really hoping we can get to optics. I love optics. I don't think, yeah, the one thing we're going to have to add here that I totally forgot to put on here, and we'll add it when we get there. So there's a bunch of formulas on the back. We got kinematics, dynamics, momentum. Oh, shoot. Yeah, momentum, I'm pretty sure is no longer part of Physics 11. I should have taken that out. And the thing I haven't added on here is any of the circuit stuff. So we'll add the circuit equations to the bottom. We've got some space down there. Yeah, we'll add those. I'm not going to reprint these. So yeah, formula sheet, don't lose those. Keep them somewhere safe in front of your binder if you want to. Yes. Angelina, good morning. How are you? Angelina, who would play you, or who would do the voiceover for the movie, for you in the movie that is your life? You know nobody. Okay. Not a single person on the planet. I'll do it. Yeah, on the front. On the filing cabinet next to Zaid. Okay, so that's formula sheet. It's yours. Don't lose it. No, up on top. Up. Yeah, there. Oh, careful. Make sure you actually look at what you're grabbing. It's the wrong one. Oh, but you're gonna need that too. Take that. Take one of each of the things that's up there. Okay, so that's formula sheet. Hang on to it. Don't lose it. Here we go. Introduction. We're gonna review. A bunch of stuff today. Hopefully it rings some bells. I've got extra practice on some of this stuff if it's necessary. We'll see how it goes. Because sometimes I assume, that we're better at things than we are. So, we're going to review a bunch of stuff. Measurement and scientific notation. Hands up if you've ever done scientific notation before. Brendan, your hand should be in there. Anyone who's in my Math 9 class, we did a little bit of scientific notation. Any of the rest of you, I don't know who your math teacher was, but you should have done it at some point over the last 4 years. Sometimes it shows up in Math 9, sometimes it shows up in middle school, sometimes it'll show up in chemistry. So, before we do that, let's talk about measurement. There are a collection of units that we call SI units. Hands up if you've ever heard of an SI unit. Manuel, what is an SI unit? No. This is not the system that the United States uses. The United States and one other tiny island country use the imperial system of measurement. The entire rest of the world, and Haiti, I think, also one of the ones. So there's 3 countries that use the imperial system of measurement, which is interesting because they had a whole Revolutionary War where they were like, no, we're not going to do this anymore, and now they still use those units of measure. No, the entire rest of the world uses SI units. So those of you who've heard of it, hands up. Really? We've not heard of SI units?
I don't know what it stands for.
Okay, it's French, because the French are all about this kind of thing. And I'm going to butcher the pronunciation because my accent's terrible, but it's like the Scientifique Internationale. It's the International Scientific Standard for Units, and you will know it as the metric system. The scientific community globally uses, well, they're supposed to, uses the same set of units so that science can be done consistently all over the world. When you don't use them properly, you have what Lockheed Martin did a couple years ago, where they programmed everything, Manuel, in American or imperial, and the entire rest of the project was done using the scientific standard units. Lockheed Martin's an engineering company. They're supposed to use scientific standard units. They didn't. And the Mars rover that was supposed to deploy a parachute over the surface of Mars didn't, and plowed into the surface of Mars, leaving a billion-dollar crater. So this is why units are important. Units, yes. Those engineers lost their jobs and never work in engineering again. So when we measure length, there is a scientific standard for the measurement of length. Do we know what it is? Anybody? What is the basis for a length measurement? The meter. We love meters. And we symbolize meters with what letter? And specifically a lowercase m. Mass, what is the scientific standard for mass? You'd think, but it's actually kilograms. Which is interesting because the kilogram isn't the base metric unit, but it is the scientific standard for the units that we use. The base here is the gram, but the kilogram is actually what we use as a scientific standard. Time. What is the scientific standard for time? The second. Which is a lowercase s. Speed. The scientific standard for speed is what? Does anyone know? Kilometers is a measurement of distance. Kilometers per hour is a good guess, but it's not ultimately correct. Speed, the scientific standard for speed, kilometers per hour is a distance divided by a time. I think someone just said it.
Meters by seconds.
It's meters by seconds, absolutely. So instead of having kilometers per hour, we use the scientific standard for distance and the scientific standard for time. It's meters per second. which we write as this. Force. Does anyone know how we measure forces? Yes. Newton's unit, yes, which is the Newton. Which we give a capital letter N to. Because lowercase n stands for something else. Energy is, sorry? Basically, yeah, joules, but yes. Yeah, because it's spelled, you're pronouncing it how it's spelled, absolutely. No, don't apologize, you're fine. That's the joule, named after French physicist, last name Joule, Joules, a capital letter J. These are the scientific standards, and there's more. There are 7 standards, and the rest of them are all built on, which we'll talk about, like when we measure current. Does anyone know the units for current? Amps or amperes, named after French physicist, last name Ampere. That's another scientific. That's one of these standards, and then everything else gets built by these standard units. There are prefixes that we use to grow or shrink the units depending on the size of the object that we're measuring. So if we want to measure something in meters, but it's really, really small, we're not going to use meters. We're going to use something like a micrometer. Does anyone know what a micrometer, the symbol for micro is? Have you seen it before, Connor? No, that's a M, like this, lowercase m. That's milli. Like mm would be a millimeter. That would get confusing. Let's do the millimeters. How are millimeters, the prefix milli, how are millis related to the standard size? Does anyone know? How many millimeters are there in a meter? 1,000. So milli means 1/1000th. So we'll put that as a fraction. Alternatively, I'll zoom this in so you can maybe see a little bit. That's as far as I can go, actually. Instead of using the fraction, we could do this in powers of 10. 1/1000th is 10 to the power of what? -3. Cool. So that's milli. We still don't have micro, but you probably know centi. Centi is, what's the symbol for centi? That's a centimeter, just the C. Because you could have centigrams, which we don't ever talk about, but they exist. It doesn't have to just be centimeters. Centimeters are just convenient because so many things are in that size range. Centi is what fraction of a whole? 1/100th, because there are 100 centimeters in a meter. Centi is 10 to the power of -2. Thank you. Love it. This without a prefix, there is no symbol if you have no prefix, but this is a factor of 1. So if I have no prefix in front of my meter, I'm just dealing with 1 of something. Kilo is, the symbol for it is, we've already used it, is K, because we have a kilogram here. And what's the factor for a kilo? 1,000. Cool. As a power of 10, it is 10 to the 3. We've got mega and we've got micro. Mega is a capital M, yep. Mega, we typically don't see those in terms of distance. As soon as it's bigger than a kilometer, does anyone know what we jump to after kilometers? If the kilometers, when we get really, really big? Sorry? A light year, yeah. Once a kilometer is not sufficient, we jump straight to light years because now we're talking about really big distances. And a light year is the distance light travels in a year, which is really friggin' far. So mega, where have we heard this prefix before? Manuel, did you just say it? You said mega mind. Perhaps. You guys are technological. Megabytes is typically in computing storage. Is typically where you hear this one, mega. Does anyone know what mega is? How many megas? How many of something if we have mega something? Nope, bigger. Sorry? A million. Or 10 to the 6. So we're still hung up on micro. The symbol for micro is this symbol here. Has anyone seen this symbol before? Where? Chemistry. As micro? Nice. So that is the Greek letter mu. We use the Greek letter mu a few different places. When we use it as a prefix, mu, this symbol here, it's a weird looking U, means micro. So the Greek letter M. No, it's a U. It's a fun U. When we use it in other places, it becomes a coefficient of friction, which is, interesting and different. Micro is 1/1,000,000th, or 10 to the negative 6. And there are more I'm going to give you on the next page. If we flip the page, you'll see that there's more, in fact, on the next page. We go all the way down to nano and all the way up to giga. And if you don't have to memorize these, I'm just going to introduce them to you here because now you'll recognize them all here. We've got kilo, we've got centi, we've got milli, we've got micro, we've got mega. But there are other ones here too. There are nanos, there are picos, there's femtos, there's yoctos, deci, deca, hecto, mega, giga, tera, peta, and yotta. In computing power, we haven't gone further than the petabyte, but it exists. And I've never actually heard of anything smaller than a femto, but sometimes we have femtoseconds, which are incredibly small measurements of time. So all of these conversions exist on your formula sheet here, so you don't have to memorize them, but we're going to start using these things. So we're going to do a couple examples. They show up when we do conversions for things. If you've taken chemistry, you've likely done conversions before. There is a method for the conversions that we're going to use. I don't know what they call it. Do they name it in chemistry? The method for converting units? There is a name for it. Okay. Well, I'll name it in the event that it shows up later. And I'm pretty sure it's going to be the same thing. We call it the factor label method. So those of you who have taken chemistry before, how would I convert something like this, 165 millimeters to meters? What's the technique? 165 millimeters multiplied by a fraction. What fraction? The meters over millimeters. Okay. So a millimeter is, so 1 meter is 1,000 millimeters. This fraction here? Okay. And now I actually go through and do this. 165 divided by 1,000. I mean, dividing by 1,000 is nice and easy. If we divide by 1,000, this shortcut is what, Jasmine? You were nodding in agreement. What's the shortcut? Well, when we divide by 1,000, how many times do I move the decimal? 3 times, because there's 3 zeros. When you're dividing by powers of 10, the decimal just slides around as many zeros as there are. 1, 2, 3. So this is going to be 0.165 meters, which makes sense, right? Millimeters are really tiny, so I'm going to have, if I have 165 millimeters and I'm making my units larger, I'm going to have a smaller number of larger units. I'm hoping that makes sense. Cool. How would I do something like this? This one's a little bit different because it goes from centigrams to milligrams, not centigrams to grams. Yeah, how would I do it? I go to grams and then to milligrams. Cool. So let's do it. I'll grab a different color here so it doesn't blend all together. Let's go to pink because pink is fun. So let's go from 380 centigrams, and I want to go to milligrams. So we're going to follow your advice. We're going to multiply this thing and we're going to go to grams. The thing I want, the unit I want to go to is going to go on top. The unit I want to cancel is going to go on the bottom because it is up top here. Like you can cancel units the same way we cancel variables or numbers in mathematics. If I'm multiplying and dividing by it, it's going to cancel out, leave me with 1. So how are grams and centigrams related to each other?
1 divided by 100.
Yes, 1 gram is 100 centigrams. So what that's going to do is that's going to cancel out my centigrams, leaving me with grams, but I'm still not done because I want to go all the way to milligrams. So what's the relationship now? I want to put grams on the bottom because I have grams up top. So I want to cancel out my grams and get me milligrams. What's the relationship between milligrams and grams? So 1 gram is 1,000 milligrams. So the 1,000 goes with the milligrams, the 1 goes with the gram. Basically what I've done here is I've taken this fraction and I've flipped it. What that's going to let me do is it's going to let me cancel my grams. And now I just do the math. 380 divided by 100 times 1,000, or I could make this a little bit easier because we're dealing with powers of 10. Dividing by 100 and multiplying by 1,000. I can do some canceling here. That's the same thing as 380 times what? Times 10. Got my 380 times 10. That's going to give me 3,800 milligrams. How do we feel about this technique? Hands up if this is a brand new technique for you. Never seen this before. Okay, cool. If you've taken chemistry, you've likely seen it, but if this is, and again, in chemistry, it gets ugly, right? Like you do this with densities and mole conversions and all sorts of other stuff in Chem 11. In physics, it stays much nicer, but if you've done it in Chem, you'll be fine. If this is brand new to you and chemistry is in your future, it gets worse, but I don't think it's too bad. I've got extra practice for you guys with this as well. So the last one, the biggest one that's probably going to be more relevant to us, involves times and distances. So we're going to jump straight to the ugly one. I want to go from 24 meters per second to kilometers per hour. So let's write it out. I'm going to grab a different color. I'm going to go 24, and I'm going to write this out as a fraction, meter per second. And I want to put this thing in kilometers per hour. So this is a composite unit. This unit is built of multiple, like 2 different units. We've got meters here, and we've got seconds here. So we don't have to convert them both at once, but we do have to convert them both eventually. It's like when you're doing density if you took chemistry. A gram per milliliter or a kilogram per liter for density, you'd convert them in steps. So we're going to convert this one in steps as well. Which one do we want to convert first? Do we want to go from meters to kilometers or seconds to hours? Meters to kilometers is the easy one. Okay? So which unit is going to go where in this fraction? Kilometers up top, because we want, kilometers, not kilograms, because we want kilometers in the top and we have meters up top. So kilometers is going to go up top. And that's going to put meters in the bottom. That's going to help me cancel my meters. How are kilometers and meters related to each other?
1,000 times.
1,000 times. So where does the 1,000 go? That would say there's 1,000 kilometers in a meter. So 1,000 meters in 1 kilometer. Okay, cool. So that's going to get rid of my meters and give me kilometers. Now I have to deal with time. I have seconds on the bottom, so I want to get rid of that, so I want to put seconds on top. Do we want to go straight from seconds to hours, or do we want to do an intermediate unit? We can go to minutes, sure. We want to go to minutes, we go to minutes. How are minutes and seconds related to each other? There is 60 seconds in 1 minute. So that's how we're going to fill out the fraction. There are 60 seconds in 1 minute. And now we don't want minutes on the bottom, we want hours on the bottom, so we're going to put minutes back up on top. How are minutes and hours related to each other? 60 what? 60 minutes in 1 hour. Cool. So now if I go through and I do this, my meters have canceled. I'm left with kilometers. My seconds are going to cancel because I've got them on top and bottom. My minutes are going to cancel top and bottom. I'm left with hours on the bottom and kilometers on top, which is going to give me my kilometers per hour, which is sweet. So if I do the math, what do I get? Y'all going to want calculators out because I'm going to get you to do calculations. I'm just going to tell you what they are. So what is it? You multiply across the top and you divide by whatever's in the bottom. So you could set, depending on how comfortable you are with your calculator, I would do, 24 times the 60 divided, 60, multiplying across the top, dividing by, I've got a 1, and a 1,000, so I just have to divide by the 1,000. If I had multiple things down here, I would throw brackets down, and I would write it like 1,000 times 1, but putting the brackets around here means that I would be dividing by everything multiplied together in the denominator. If you do that, what do you get? 86.4? Sweet. So 24 meters per second is 86.4 kilometers per hour. Now, I am not going to require that you go through all of these steps every time. There's a shortcut for this. What is this piece of the question equal to? What is that? Sorry? It's 3.6. So if you knew that, 60 times 60 is 3,600 divided by 1,000 is 3.6. The shortcut then means I could have just, because I'm multiplying here, I could have just multiplied my meters per second by this factor to go straight to kilometers per hour. And that is going to be a nice, quick, little convenient number for you to hang on to. So we're going to put it in this box here. If you're going from meters per second to kilometers per hour, you're going to multiply by, we're going to put 3.6 in the middle here. If you want meters per second, 2 kilometers per hour, you're going to multiply by 3.6. So what do I do if I'm going the other way? What if I'm going from kilometers per hour to meters per second? Sorry? You divide it. So this little box here is going to be a handy dandy thing you're going to want to know. Should you, be allowed to, make a cheat sheet in the future? Putting that on there might not be a bad idea. So this conversion factor is going to be really, really useful for everything you do going forward here. Comments, questions, concerns about any of this? I will post some optional practice. If unit conversions are something you're like, yeah, I don't know how I feel about this, there's going to be a couple questions in here in the stuff that I'm going to give you when we get to this lesson part down here. I'll give you some density stuff, and I'll give you a formula for density. Oh, actually, do I even do that here? No, I don't. No, I don't have any practice in here on unit conversions. If you want practice, I'll be posting it into the Google Classroom. It'll be entirely optional for you if you want to take a look at that there. Hands up if you would find that useful. Okay. I will do that. Maybe I should give you some class time to do that then. Yep, script. Let's do that. I'll print it off right now, and you guys can do some unit conversions. For those of you who have taken chemistry last semester, this will be really easy and a nice, great little refresher on this stuff. Let's do it. Where did my unit conversions go? Okay. Oh no, they're here. Okay. Okay. We're going to print this. Okay, while we're waiting for that to print, it's built into this whole idea of unit conversions is I've also got a section there on scientific notation, so we're going to take a look at this as well. I'm hoping scientific notation is review for you. I understand if it might not be. So scientific notation, we use scientific notation to do what? What's the purpose of it? Make stuff look nicer. It ultimately means we can write less, because when we're dealing with things in physics, the values can get really, really, really big, having lots and lots and lots of zeros hanging off the end, or really, really, really small, having lots of zeros between the decimal and our first number that actually matters. So scientific notation is something that we use to handle this. So instead of writing 32 million, scientific notation would say, how would I write this instead? For those of you who have seen scientific notation, what are we doing here? Sorry, Manuel? Almost. With scientific notation, what you want to do is you want to have one value, one digit, and then a decimal place. You want one digit, a decimal place, a couple more digits, times 10 to the power of whatever. And how you get that power will determine on which way you move the decimal. Okay, so if I have 32 million here, there is no decimal place written in 32 million, so where do we automatically know it would go if we were to put one in there? It'd go at the end. That doesn't change. 32 million is 32 million with a decimal place. That doesn't matter. So now what I'm going to do is I'm going to say, okay, to get a format that looks like this, one digit, a decimal place, and then some more digits, we're going to start where we were here at the end, and we're going to go over 1, 2, 3, 4, 5, 6, 7. So we're going to get 3.2. The whole point of the scientific notation is to get rid of those zeros. We don't want to include them. So we're going to have 3.2 times 10 to the power of how many decimal places we moved. In this case, we moved how many? 7. So it's going to be 3.2 times 10 to the 7. If I actually did this multiplication, I'm hoping you would recognize that this thing would get, this number, 3.2, would get large very, very quickly. Because 10 to the 7 is a large number. What happens if I go the other way? If I have a really small number, 0.0000436.
There's any problem if I put 32 multiplied by this
The short answer is yes. The scientific standard is to have a single and then everything else is the standard. Now, that's not always useful. Sometimes it would be more useful to have 32 times 10 to the 6. So I'm going to teach you the standard, but I'm going to tell you that it's flexible. So standard would be 3.2 times 10 to the 7, but you want 10 to the 6. Why do you want 10 to the 6?
Because I was like, it is 32 by 10, so that is, no, 6.2 by 10, so I don't know, it's easier for me to put. Instead of the 3.2, the 32. Yeah, that's it.
Yeah. Oh no, I know. Sorry, I do know that. That's it. The standard for scientific notation is to have a single digit, decimal, and then everything else. But there are times where this is more useful, especially when we have things like 10 to the 6. We have a unit for that up here. So we don't have if I have 3.2 times 10 to the 7, whatever. If I have 32 times 10 to the 6, I'll say it's meters. 32 times 10 to the 6 meters, that's a really easy conversion. Instead of having 32 times 10 to the 6 meters, I now have 32 megameters, because the power of 10 that we're using can get converted into a unit we have a nice conversion for. But the scientific standard, yeah, I've said it before, the scientific standard is a single digit and then the decimals, but there's flexibility there. Certainly use it. So this one down here, 0.0000436. We're taking the decimal and we're moving it now 1, 2, 3, 4, 5, 6 places. That's going to give me 4.36 times 10 to the what? This number is very small, so my exponent on the 10 is going to be negative. And how many spots did we move? I moved 6 spots. 6. So that's going to be 4.36 times 10 to the negative 6, whatever those units are. So that would be a micro something if we wanted to convert the 4.36 micro whatever, if we wanted to, because we have a nice conversion, 10 to the 6 and a 10 to the 6. So we've got the standard for scientific notation, move the decimal point until only one leading digit remains. The number of spaces moved becomes or is the exponent. When we move the decimal place to the left, the exponent was positive. When we move the when we move the decimal to the right, the exponent was negative. So Luis, if I ask you to put things into scientific notation for me, this is what I will want to see. If you're using scientific notation to do other work and I don't care about the intermediate step, be flexible. Okay? So, do this. Take a look at these. Real quick here. hands of, oh, your side is still going. Yes, sir. For number 3, hold off on number, if you blasted through 1 and 2 already, for 3, I want you to do them without a calculator.
Yeah, I know the one. I was asking to the answer to the E without expanded or the power up.
Leave it in scientific notation. No, someone else, oh, yes. I thought someone else just asked to go. Sorry? Okay. Okay. Let's do this. Done. Okay. Okay, how do we feel about this stuff? Relatively simple, yes? Okay, so first one should be what? 5.5. 5.5 times 10 to the 9. This one's going to be 7.8 times 10 to the 2. C is going to be 9.1 times 10 to the negative 2. This one's going to be, sorry? Careful, there's a 3 there. 3.004 times 10 to the power of negative 6. Good. Going the other way, we didn't talk about that in here, but I'm hoping that the technique is obvious. When I've got a negative exponent here, the number is going to be getting smaller, so I'm going this way. So 5.5 times 10 to the negative 4 is what?
0.00055.
How many zeros should be there? Got to be careful when you're doing the moving. It should be 3 because the decimal starts here and you move it the number of the exponent. So if it's -4, we're moving it 4 times, so it's going to be 1, 2, 3, 4, and it's these empty spots here that then get zeros. And then the decimal shows up. So it's 0.00055. This guy here, 7.1 times 10 to the 6. 7, 1, and then followed by 5 zeros, which is 7,100,000. And then 1 times 10 to the 3 is 1,000. Cool. I just wanted you guys to take a look at this box here, 1 and 2. Hands up if you did these ones already here. Okay, cool. These ones just require that you have a remembering of your exponent laws. So what am I doing here? If I've got 10 to the 3 times 10 to the 5, we're adding exponents. When you're multiplying the same base, you add the exponents. So this is going to become what? It's going to become 10 to the 8. Thank you. 3 plus 5 is 8. Love that. This guy here, 10 to the -3 times 10 to the 5. When I'm multiplying, I'm adding. This becomes 10 to the 2. Love it. This guy here, when I divide bases, I do what with the exponents? Subtract them and I go left to right. So this becomes 10 to the power of 3 minus 5, which is what? -2. I got 10 to the -3 divided by 10 to the 5. So what's that going to do here?
So the negative is going to be the positive. So
careful. It's left minus right. So it's -3. This is going to become 10 to the -3 minus 5. Because when I divide my same bases, I subtract my exponents. And I work left to right. -3 minus 5 is going to become 10 to the -8. Cool? Does that make sense? Be careful when you operate in your head. The temptation is to get sloppy. Don't get sloppy. Okay. I put a couple more up here for you because we don't just operate with powers of 10. We do this with values in scientific notation. So how would we tackle something like E? Yeah, Manuel, what are you doing?
You distribute the outside exponent into each base.
Why can I do that?
Because math,
There's a very specific rule why I'm allowed to distribute this exponent onto everything in the bracket. Sorry? No. Jasmine? Why is it being multiplied to everything? It's not being multiplied. It's being applied to everything in the bracket because... Why, Connor?
because it's around it and everything needs to be put together. It is other.
So if I had this, could I, if I had this,
No.
would I be able to distribute this exponent onto everything in the brackets?
Oh, because you'd have to do what's in the brackets first.
But you're telling me I don't have to do what's in the brackets here first. What's the difference between this and this? I'm multiplying here. And an exponent is just a shortcut for multiplication. Because I'm multiplying in here, I'm allowed to apply the exponent. I am not allowed to apply the exponent here because I'm not multiplying. An exponent is not a shortcut for addition. Okay? So this can't distribute. Just so we're real clear. But here I can. So I'm going to. When I have a product to a power, what's going to end up happening to my exponents here? I multiply my exponents together. So this is going to become 3 squared times 10 to the, and then 8 times 2 is 16. So what's that going to be? I can leave it in scientific notation, so there's actually no need for a calculator for this question because the only math now I have to do is what? 3 squared, which is 9. So it's going to give me 9 times 10 to the 16. This guy here, we're going to do it together. Unless you rushed ahead, great. Make sure we're following along with what we're doing here. Anyone with an idea, where can we start with something like F? Manuel, your hand was first.
Can you multiply it like that? Or
Yeah, because this is all just multiplication. Absolutely. This is the same as 8.0 times 10 to the 5 times 1.2 times 10 to the 8. Yes, I can move stuff around here. You betcha. Is that the smart thing to do first? If I asked you to do this without a calculator, could you do it? You just did. What did you do, Manuel?
Well,
What's 8 times 1.2? It's 9.6? How do you know it's 9.6? Well, you just multiply it on paper. There's a shortcut for this. Yeah. If you don't want to multiply it in your head, you can, like Luis wanted to do earlier, I can move stuff around here. If I have 1.2 times 10 to the 8, I could make this 12 times 10 to the something. 1.2 times 10 to the 8 is the same as 12 times 10 to the what? To the 7. Who said that? Yes, that is correct. If I move my decimal to the right, my exponent drops 1. So 1.2 times 10 to the 8 is the same as 12 times 10 to the 7. So then this thing could become 8.0 times 10 to the 5 times 12 times 10 to the 7. Y'all better know what 8 times 12 is. Thank you. I heard it in the back. That becomes 96. And then I can do the 10 to the 5 times 10 to the 7. 10 to the 5 times 10 to the 7 is going to give me what? Is this thing in proper scientific notation? No. So if I asked it in scientific notation, what would you then have to do? I'd have to move the decimal over back into between the 9 and the 6. So that's going to give me 9.6. And when I move my decimal to the left, what happens to my exponent here? Sorry? It goes up 1. So this is going to be 9.6 times 10 to the... Cool. Comments, questions, concerns on what just happened here? Cool. This guy. What am I doing here? Got to be careful with how we deal with things when we've got division hanging out in the middle. This thing is the same as this. So how would I handle this? Manuel. What do you mean?
Because the right the right term is over 1. If we just multiply it and then flip it, then multiplication is easy.
I'm not sure what you mean. Because this is what we have. I've got 2.3 times 10 to the negative 3 divided by 1 times 10 to the negative 5.
That's what I meant. You did it.
Oh, I just did it.
Skip some steps, yeah.
Oh, I skipped some steps.
Yeah.
Oh, then I understood what you said to be very different than what you meant.
No, that's what I did. I was just like getting more steps.
So you just turned division into the fraction
I
here.
just saw them as fractions and then I flipped them and then combined it like the multiplications across. You just did it like in one go. Yeah.
Okay.
Okay.
So how would I deal with this thing?
Same way you did the last one.
Same thing I did the same way I dealt with the last one. So I can deal with this. That's just going to give me 2.3. And now I can deal with this. 10 to the negative 3 and 10 to the negative 5. If I'm dividing these two, that's going to give me what? Yeah, Connor? Not 8.
Oh, okay.
Remember, I'm subtracting. What is negative 3 minus negative 5? It's 2. Go back to our exponent laws and addition and subtraction. You gotta be careful with how you add and subtract things. Last one. I got 4 times 10 to the negative 3 times negative 5 times 10 to the negative 5. This looks a lot like f. I can multiply these two, and I can because all I'm doing is multiplying, I can multiply my digits out front by, or my numbers out front of the scientific notation by my powers of 10. And I can do those separately. So 4 times negative 5 is going to be negative 20. And 10 to the negative 3 times 10 to the negative 5 is, I'm multiplying bases, so I'm adding exponents. That's going to give me 10 to the negative 8. That's not in hold on. It's not in scientific notation, so how do I finish that thing off? I move the decimal. When I move the decimal to the left, what happens to my exponent? It goes up 1, and so from negative 8 to going up 1, we're at negative 7. Cool. So it's negative 2 times 10 to the negative 7. The only thing I want you to do for homework, I posted some extra practice of unit conversions. I will be giving you class time to work on those, so you don't have to do those. The one thing I want you to do for homework is this column right here. I want you to estimate, don't look anything up. Estimate objects of various sizes using these different powers of 10. When you think of a power of 10, what size do you think of something? And we'll do the rest of this tomorrow. Just this column here, that's what I want you to do tonight for homework. Have a great day, guys. We'll see you tomorrow. Yes, Manuel.
For the last one,